welcome. How's everybody? Good. Okay. So just wanted to go over our schedule for the next few weeks as we get closer to final exams. This is pretty much final at this point. Things kind of evolve over the semester, but I think this is what's going to happen as we get into finals. So today we'll finish chapter 7. We'll start chapter 8. Tuesday we will continue with chapter 8. Then we have a mini spring break next week, next Thursday. And then April 19th will be a Tuesday, so we'll do an in-class review just like always over chapter 7 and 8. April 21st, exam 4 over chapter 7 and 8. Then last week of April we'll get into chapter 9. And then the final will be on that Wednesday, May 4th, 8 to 9:50 over chapter 9. So, any questions? Good? Okay, so remember with our spring break next week, we don't have labs. So what we did on this week we'll be due in 2 weeks. So we'll pick it up with labs this week, April 18th through the 21st, because there's that Monday lab. We'll meet in YSHB 134. We'll do some stuff with the data we collected this week with the jump. Your study guide for chapter 7 and 8 has already been posted, so you can see that in the study guide folder and get started on that. Any questions? Okay, all right. So with that, I'll close this. All right, so let's have just a little bit of a warm-up. Everything in chapter 7 is the same as chapter 3. Only chapter 3 was all about linear motion due to force. Chapter 7 is all about angular motion due to force. So we have the same concepts, it's just thinking of things in an angular sense rather than a linear sense. So in a linear sense, mass is equivalent to inertia. Okay, so mass in kilograms from a linear standpoint promotes greater resistance to change in linear motion. How is angular motion different? So how is angular inertia different than linear inertia? So linear inertia is just dependent on how big an object or body is. So a more massive object or body will have more resistance to change. How is angular inertia different? So resistance to rotation. Is mass an important factor? Yeah, mass is still an important factor. What else do we have to consider with angular inertia that we didn't consider with linear inertia? So if I'm doing a squat and I have a plate right here that I'm squatting with, and I'm holding the plate right here as I'm squatting, and then I change and I hold the plate out here, okay, what part of angular inertia changed as I go from this position to holding the plate out here in this position? So mass multiplied by, it's kind of a funny term, the radius of gyration. Remember that, radius of gyration? So we have to consider the distance between the axis and where the mass is concentrated, right? So the formula for angular inertia includes 2 parts. So mass is one part, but we also have to consider where the mass is distributed relative to our axis of rotation. So which of those 2 factors is more important in determining angular inertia? Is it the mass or is it the radius of gyration that's more important? Yeah, and so We know that because in that formula, radius of gyration is squared. So if we double the distance between the axis and where the mass is concentrated, we quadruple the angular inertia because that radius of gyration is squared. So I is equal to mass multiplied by, what's our symbol for radius of gyration? It's a k, so k squared. Okay, so in the same way, we talked about angular momentum. So linear momentum is equal to what two things multiplied together? Linear momentum with a capital L, you have your mass, and what else? What else determines momentum? How big something is, and what else? Yeah, so how fast it's moving. So linear momentum, mass multiplied by velocity. Angular momentum, and we use a capital H for angular momentum, is equal to not mass, but our moment of inertia, which is like mass, only from an angular sense. So mass, moment of inertia, multiplied by angular velocity. So remember, angular velocity is that little, kind of that W-looking Greek omega symbol. So angular momentum, so the momentum of an object or body that is rotating, is dependent on the moment of inertia, which is mass multiplied by radius of gyration squared, multiplied by angular velocity. So as we continue on today, and as we talk about torque and impulse, all these things that we previously talked about in chapter 3 are going to come up, but it's thinking about rotation about an axis rather than movement from a linear standpoint. So I like to focus on the application because you're all going to be out there in the field as practitioners, so we want information that we can use and see things and how they apply in the real world. So this would be angular application of Newton's first law. So the Newton's first law of motion is oftentimes called the law of inertia. Yeah, so from an angular standpoint, an object or body will continue rotating, or it will remain at rest unless what? What do we have to have acting on a body or object to make it rotate? We have to have not a net force, but what's a force that makes an object or body rotate? What do we call that? In other words, a force that is applied off-center. Not through the center, but at a certain distance. Yes, that's an eccentric force, which we sometimes equate with torque. So an object or body will remain at rest or continue rotating at a constant angular velocity unless we have a net torque. So if the net torque is not equal to 0, if there's an imbalance in torques, then we're going to have a change in how an object or body is rotating. So that object or body will either rotate faster, or it will rotate slower, or it will change its axis of rotation. So remember how many axes we have about which an object or body can rotate? So we listed them on Tuesday. So you have 3 planes, and each plane has an associated axis. Remember the ones from our textbook? So we have the sagittal plane, which involves rotation about which axis? Transverse. Okay, we have the frontal plane, which involves rotation about which axis? Yes, anterior, posterior. So remember, there's several names, so we'll just use the ones that are with this book, and then when you have me for kinesiology, you can change, because we use a different book. So transverse plane, which axis? Yeah, longitudinal. So again, there can be multiple names for axes will be consistent with this textbook. So we have a hurdler here today who has experienced this. So with sprinting and hurdling and all these awesome sports skills, we have torques that are placed on the body based on how our limbs are positioned. So in this case, we have reciprocal actions of the arms and legs. We have reciprocal actions of the arms and legs in hurdling, and we also have reciprocal actions of the arms and legs in sprinting. So why is it that if we have one side of the body doing one thing in one direction, we have to have the opposite side of the body doing another thing in the opposite direction? So again, Newton's first law, to keep the torso from rotating, we have to have equivalent what? Around the body's axis, we have to have equivalent torques. So the net torque acting on the body has to be equal to 0. So that's what we want. If we have one leg that's up here, we want one leg up, or one arm up here. If we have a hurdler moving the left leg forward, and so you have to imagine this leg's going to whip over the hurdle like that, then we have to have the right arm move back. And so we have equal and opposite torques that act around the axis of the body. And because torques are equal and opposite, that's a good thing, because that's what keeps our bodies squared up as we continue going over the hurdle or sprinting around the track. So with Newton's first law, good test question, with Newton's first law, the net torque acting on a body is equal to what? 0. Okay, that's exactly right. So a body or object will remain in equilibrium. It will continue in its constant state. Hey, Trace. As long as the net torque is equal to 0. So moving into Newton's second law, what's the real difference? Doesn't matter linear or angular. What's the real difference between Newton's first law and Newton's second law? It all has to do with the net torque. With Newton's first law, the net torque is equal to what? We just said it. It's equal to 0. With Newton's second law, what's Newton's second law called a lot of times? Not the law of inertia, but the law of acceleration. So now, in order to have an acceleration from a linear standpoint or from an angular standpoint, the net torque is no longer equal to 0. And so the magnitude of the net torque determines how much angular acceleration we have about an axis. So I'm going to pause right here because we've got Trace here, who's one of my thesis students, and he's doing an awesome study on a variation of the star excursion balance test. So I'm just going to invite him to come up and talk about his study, and you have an opportunity to help out. So Trace, take it away.
Like I said, I'm Trace. I'm a thesis student right now. I've had classes with a couple of you guys just to ask who's an athlete in here. That's why I wanted to come in here. So I'm only studying athletes right now, just to make my study a little bit more specific. So I'm just talking to you guys. Pretty much all it is. Have you guys done the star excursion balance test yet? You did? Okay. So we're gonna do that, but it's gonna be a modified one. It's only 3 directions as opposed to the 8.
Only 3.
So it's not as much of a workout. Pretty much I'll have you come in, you'll be on a treadmill for a minute, and then I'll measure your leg just like we did in the lab, and then I'll test you initially what your score is, and then we'll use the vibe plate or the whole body vibration plate, so that way we can see what the effects of whole body vibration are on the test scores. It'll be 2 different sessions, so if you guys are interested, just like raise your hand. I'll pass this around. I'll get in contact with you. If not, that's fine. I'm just looking for a few more people. be pretty easy, it'll take like 20 minutes, so.
I think we've had the whole body vibration platform once in lab, and we've done the star test, so. So what frequency of vibration is it?
So we're doing 30 and 60, I believe.
Oh, wow, 60.
Yeah, I think that's what I decided on. It's either 30 and 60 or 20 and 50. I can't remember the exact number, but.
So the effect on your score. Interesting.
We're both in season right now, so it's gonna be kind of everywhere for those.
I'm sure. Are you guys in town this weekend?
Yeah, this week.
Okay. Will you be available on Saturday afternoon? No.
Yeah, we got 2 games.
Okay.
Yeah, sorry.
That's all right. We'll figure it out. I knew the risk I was
Trace,
taking.
if there's another, like a weekday or something, we can work it out.
Okay.
Weekdays.
Everybody in the 105 class, I think they were all right with doing Saturday, and Logan was gonna do Saturday. I knew the risk I was taking.
There's weekdays.
Oh.
Yeah, I'm pretty excited to start doing
Yeah.
collection.
This is the last step.
Yeah. And then, my defense is the 25th.
We're trying to get everybody at once in the 20th. So everybody together and send you out.
So, so I'll have like 9, is that enough, or do you want me to?
You know, I think 9 is great.
Okay, that's good.
That sounds good.
So I talked to Dr. Shaper too, and he said that you talked about it in his class and see if anyone wanted to come, but. Okay.
Yeah, that 9 is good.
I just didn't want to have too few.
So our first session's Saturday. Okay, I'll be there.
And where's it gonna be set up?
Let's meet at my office first over there.
Okay.
And we'll set it up.
Do you want me to come in on like or tomorrow and like actually set up the tape and stuff, or?
We can do that.
Okay.
Yeah, that'll take just a few minutes.
Okay, I'm like, cause I don't wanna waste time.
Yeah. Okay.
It's right here.
Oh, there it is.
Got it. Okay.
Cool. Thank you guys.
Trace. Thanks, everybody. Okay. So back online. So we have Newton's second law, where the net torque is not equal to 0. We have an acceleration from an angular standpoint. So spinning faster or slower or changing the axis of rotation is what angular acceleration means. Okay, so this is the mathematical expression of Newton's second law from an angular standpoint. So remember, from a linear standpoint, it was sum of force equals mass times acceleration. From an angular standpoint, it's the sum of torque, capital T for torque, is equal to, remember what I is? Yeah, it's not mass, it's the moment of inertia, which is what two things again? Do you have to factor into the moment of inertia? The mass, but also what other factor that's more important? Getting there, that's on the end. That alpha is acceleration, so you're there. But what other factor with moment of inertia besides mass? Yes, so how the mass is distributed, and we square that. So the net external torque, the moment of inertia, so again, mass times radius of gyration squared, and then the alpha symbol there for angular acceleration. So this is instantaneous. So we're not talking average acceleration over a time interval. This is the moment that the acceleration takes place is proportional to the net external torque. So in order to have acceleration of a rotating body or object, we have to have a net external torque that's greater than 0. is the key point. So, do you remember in chapter 3 when we talked about the impulse-momentum relationship? So in chapter 3, we talked about how when a net force is applied over a time interval, we have a change in momentum. So momentum can increase or momentum can decrease. Like, remember we talked about the egg toss? That's an example of reducing momentum over a time interval, okay, by absorbing the force, okay, or when a pitcher like Logan winds up, the time of the windup allows him to build force so that the ball has the most momentum or velocity when it's released. So really with momentum, whether it's linear or angular, we're talking about a change in velocity. That's what produces the change in momentum. So the angular impulse momentum relationship is the same as the linear impulse momentum relationship. It's just, in this case, impulse is equal to a net torque that's applied over a period of time to cause a change in angular momentum. So again, a net torque applied over a period of time. So just like linear impulse, net force applied over a period of time. This is a net torque applied over a period of time that causes a change in not linear but angular momentum. So let's review, what's angular momentum equal to? It's a little bit different than just mass times velocity. It's angular momentum is moment of inertia times angular velocity. So the difference is in that how the mass is distributed versus with linear momentum, it's just mass. Okay, so here's your formula right here. So again, so a torque, that's a net torque, applied over a period of time results in a change. So the little triangle there, that's called a delta, and that means change. So a torque applied over a time period or a change in time equals a change in momentum, angular momentum. So notice with angular momentum, we can have two parts. So an object or body can have a final angular momentum, and an object or body can have an initial angular momentum. So we can apply a torque over a period of time to bring a rotating body or object to a stop, in which case the initial would be greater than the final, because if you're bringing a rotating body to a stop, what would final angular momentum be? It'd be 0. So we can also apply a torque over a period of time to bring an object or body that's at rest into motion, where they would be rotating, in which case initial angular momentum would be 0, because we're applying a torque over a time period to initiate rotation. So I was trying to think of how can I apply this. So I think I found the perfect link. So let's watch this, and then I want you to think about, with this video, I want you to think about how this concept applies. And as soon as I pull this up, you're going to smile, because I know a lot of you have seen it.
In the movie Happy Gilmore, Happy converts his hockey swing into a golf swing to get insane distance off the tee. drives over 400 yards. But does this actually work? Is it a Hollywood trick? Or could someone actually get extra distance off the tee, hitting like Happy Gilmore? To find out, we brought in the only person who was willing to try such a bizarre swing. A golfer who also happens to be the 2008 PGA Player of the Year, Padraig Harrington. In 2008, this Irishman won 2 majors, the British Open and the PGA Championship. Like Padraig, every professional golfer on the planet hits a tee shot the same way, standing still. But surprisingly, there's nothing in the rules that prohibits a golfer from running up to the ball.
It's perfectly legal to use the Happy Gilmore swing on the golf course. There's nothing stopping you running up.
But hitting a driver is hard enough when you're standing still. Even pro golfers only hit the fairway 60% of the time. You're trying to make a square-inch sweet spot at the end of a 4-foot-long stick, traveling 100 miles an hour, make contact with a target smaller than a dime. So that kind of precision on the rod is actually next to impossible. Padraig's not exactly short off the tee. His normal drives average 296 yards. But the idea of getting extra distance off the tee, like Happy, is tempting, even for a pro like Padraig Harrington.
The bigger a hitter you are, it is an advantage. The best player in the world always tends to be the longest hitter in the world, or close to it. He always has a length advantage.
So, could a successful Happy Gilmore swing generate more distance off the tee? And help a pro like Padraig win more tournaments? And if so, shouldn't golfers around the world rethink the way they hit golf shots? It's time to take the shackles off of golf and see if Padraig can hit a golf ball while running. Are you kidding? Padraig totally smokes his Happy Gilmore drive. And he doesn't just take a step into the ball like Happy. He gets a full-on running start.
Well, I noticed that both my feet left the ground at one point, so I was airborne.
At first glance, the two driving styles look radically different. But a side-by-side comparison on the Phantom high-speed footage is mind-blowing. Incredibly, even with a running start, Padraig's club position at the top of the backswing and at impact are virtually identical. So it looks amazing, but did Padraig's unconventional swing actually crank out longer drives? In fact, using a Happy Gilmore swing, Padraig actually does drive the ball much farther, on average, 30 yards farther. Our motion capture technology reveals exactly how Padraig gets happy. Padraig attacks the ball at 4 miles an hour. This forward momentum helps increase clubhead speed from his normal 107 up to 114 miles an hour. More importantly, his run-up enables him to make a huge shoulder turn. And This is one key to extra distance. Pros call it the X factor.
That's how much you stretch your hip away from your shoulder in the downswing. And because I plant a little bit like a javelin thrower in my Happy Gilmore, I get a much better stretch, and then my left hip stops much quicker so that I get that acceleration.
Padraig's increased shoulder turn means that he can hit his Happy Gilmore drives a full 10% farther than his normal drives. And those extra yards off the tee can mean a big difference on the next shot. If you're approaching the green from 30 yards closer, you're hitting less club, and you've got a better chance of sticking that ball near the hole. So why doesn't Padraig use this crazy swing on the golf course? It comes down to consistency and accuracy.
I don't believe I'd be as accurate. And would the gain of 20, 30 yards be worth it?
Because added distance can also mean added distance the wrong way. At impact, a club face that is twisted only 1 degree offline or makes contact a couple of millimeters away from the sweet spot can result in a drive that travels 20 yards offline.
I'd like to do it on the golf course, but I'm too cautious for that.
Ultimately, in a sport where millions of dollars could come down to 1 or 2 strokes, the risk isn't worth the reward. But for the rest of us, since we all pretty much stink anyway, even Padraig recommends we try it.
If you're going to try the Happy Gilmore, and I think you should try it, don't think too much about it and just give it a good hit.
Okay. All right, so let's put some biomechanics to that. What'd you learn? So how is the Happy Gilmore swing? Let's look at this equation. So he's swinging something. That means there's torque because there's rotation. So what's he doing with, how is he changing angular momentum? He had the same position at the top of the backswing, so he's taking more time to build torque through the kinetic chain. Remember from chapter 6, one of the key equations was the relationship between tangential linear velocity. Remember the v with the subscript t is equal to angular velocity, the omega multiplied by the radius. So for a given club head length, with the run-up, he's developing greater angular velocity. So remember, his club's head speed in miles per hour is greater. So that automatically results in a greater impact velocity. The third concept was the stretch-shorten cycle. Remember stretch-shorten cycle, where all of our actions, or at least most of them, begin with a load phase, where we're stretching muscle and storing this elastic potential energy that we can then apply to the movement phase. So what was different about the Happy Gilmore swing that would apply to the stretch-shorten cycle? Yeah, so stretching one hip further away from the back shoulder, they call that the X factor, right? So there's more storage of elastic energy, and then if we have that short amortization between the top of the backswing and beginning of the downswing, we automatically get more power into the swing. So it's kind of entertaining, but there's a lot of truth and mechanics to what we saw there. Okay, so for activities that require quick rotation, we generate torque, okay? And technique is a really important part of this. So in throwing a discus, an athlete will begin with a larger moment of inertia. So do you remember from Tuesday what the relationship was between moment of inertia and angular velocity? So the figure skating example with their arms out here, they have a larger moment of inertia because more of their mass is distributed away from their axis. So larger moment of inertia means what for how fast you're spinning? Slower. Okay, so at the beginning phase of a discus throw, an athlete's going to have their arms spread out more. And so we call this the torque generation phase. The torque generation phase. So if you have a slower, if you're spinning slower, you're able to take more time to build that torque through the kinetic chain. And then as we go on through the throw, an athlete will bring their arm, the non-throwing arm, in close to the body, which reduces the moment of inertia and does what to how fast they're spinning. Yeah, so they're going to be spinning faster. So, so the initial part of a discus throw, we call that the torque production phase, and then they bring the one arm in, and they're spinning faster just prior to release. So we can see that here with, it's the same thrower, a world-class discus thrower, but you can see here, this is the torque generation phase, and so their mass is spread out a little bit more, so they're taking more time, they're spinning a little bit slower, so they're building that external torque that they can put into the discus, and then and then as they get ready to release, they're pulling the non-throwing arm in, and that increases how fast they're spinning, and that puts that speed on the discus as they release it. So I think this lady's from Croatia. I'm not sure. She held the world record at one time, but I have to check and see if she still does. Okay, so let's go ahead and get a practice problem like we usually do. So this is one for figure skating. Okay, so Sarah's angular momentum increases from 0 kilogram meters squared over seconds to 50 kilogram meters squared over seconds. Okay, so this would be the final angular momentum here. So the initial angular momentum would be equal to 0 because she's not spinning. So we have to be spinning to have angular momentum. So the final angular momentum is 50 kilogram meters squared over seconds, and she goes from 0 to 50 in 0.25 seconds as she initiates a twisting jump in figure skating. At 0.25 seconds, her moment of inertia about her twist axis is 2.2 kilogram meters squared. Okay, so in this case, you're given two questions. So let's take the first question, part A. How large is the torque that produced the change in angular momentum? So this is our angular impulse, angular momentum relationship. So a net torque applied over a time interval equals a change in angular momentum. So because our initial angular momentum is equal to 0, so she's not spinning yet, the only relevant factor would be her angular momentum at 0.25 seconds. So we're using our angular impulse, angular momentum relationship. We have a torque applied over a time interval, which is equal to the change in angular momentum, but because the initial is equal to 0, we can just consider the 50 kilogram meters squared over seconds. And so in this case, the way that we're setting this up, we're asking for torque. So when you do this problem, how do we solve for torque? So we have torque multiplied by time is equal to our final angular momentum. And so to our final angular momentum divided by time. Okay. So what was our final angular momentum again? It was something like, what was it, 50, what are the units? Kilogram, meters squared over seconds. And then we're dividing that by how long was the time interval over which that took place? Remind me, so 0.25 seconds. Okay. And what are you coming up with? 200. Okay, now, what are the units for torque? If we're talking torque, what units do we have? Yeah, Newton meters. Newton meters. So how do we get a Newton meter out of this right here? Well, if we consider 1 Newton is equal to 1 kilogram meter per second squared. That's another way of thinking about newtons. 1 Newton is equal to 1 kilogram meter per second squared. But isn't it easier just to say newtons? So if we wrote it like this, if we wrote 200, what we have would be kilograms meters squared over seconds squared. If we took all of these variables at once, we could say 200 kilogram meters squared over seconds squared. Okay, so if we substitute just Newton in there, what are we left with? If we substitute Newton in here, what are we left with? So seconds squared is gone. What about kilograms? Yeah, kilograms is gone. How many m's do we have here versus here? We have 2, so we still have that there. So we're basically able to get it down to just a Newton meter in torque. So that's how we come up with Newton meters from all of those different variables. Does that make sense? No. So 200 Newton meters is our units for torque. So do you have any questions on how we came to that one? Okay. All right, so let's keep going. We're almost done with chapter 7. Okay, so Newton's first law, Newton's second law, and then all we have left is Newton's third law, right? So rather than force, if it's angular, it's not force, it's torque. So Newton's third law can be stated like this: for every torque exerted by one object on another, the other object exerts an equal torque back onto the first object, but in the opposite rotational direction. So Newton's third law, think about for every torque, there is an equal and opposite reactive torque. So this is applied to bodies or objects that are spinning. So just as we saw with Newton's third law in the linear application, the effects of these equal and opposite torques depends on the moment of inertia of each object. So an object or body that has less moment of inertia will be impacted to a greater degree by a given amount of torque. Just like in a linear sense, an object or body that has less mass will accelerate to a greater degree for a given amount of force. So it's just thinking of things in terms of rotating versus just moving in a linear sense. Okay, so very last slide. So how many of you have done something like this type of exercise? So let's see if I can mimic this here. So left leg and the left fist, and then here, and then I need to work on my balance. So just like this. So there's a couple of different torques that are applied. There's an anterior-posterior torque. So that would be through the sagittal axis. So there's going to be a tendency for the body to want to tip in this direction. So that would be the sagittal plane. What was the axis for the sagittal plane? The transverse axis. So there's also a torque acting on the body due to the weight that's going to do what? It's going to tend to want to rotate the body. Rotate the body in this direction, right? So that would be the transverse plane with the longitudinal axis. So we have to create tension in our muscles, and we have to have really good proprioception to feed back into our spinal cord with muscle spindles and so on that are creating quick contractions of those muscles to keep our balance and resist those torques. So gravity is what creates resistive torque, and our muscles create torque in the opposing direction, just like Newton's third law. For every resistive torque, in order for you to maintain balance, we have to have an equal and opposite torque from our muscles, right? So if our muscular torque isn't matching the resistive torque, what's going to happen? We're going to lose our balance. So muscles create torque that opposes resistive torque from gravity. So do you have any questions on chapter 7? I feel like you have a pretty good handle on moment of inertia, angular momentum, angular impulse. Okay, all right, so let's, how are we doing on time? 9:30, okay. So I have a student that's collecting their project data at 10. This is like the week of research down in the lab, so we'll go for maybe about 25 more minutes. So chapter 8. So chapter 8 is on fluid mechanics, the effects of air and water. So I love this chapter because there's so many applications. And let's begin with just a little bit of a discussion. So what factors affect air resistance? As you look at this cyclist and all of these, that high-tech bike and that high-tech clothing, so how are they able to minimize, we could say, fluid resistance? Because fluid can refer to air or water in a mechanical sense. So what are some things that you notice here that are obvious that cyclists do to minimize fluid resistance? Or sometimes we can call it drag resistance. Drag resistance, fluid resistance. So what about their helmet? That has a nice streamlined shape, so the air slips over the top and then off the back. Okay. So what else? What else do you notice? Come on. Yeah, posture. So they're in kind of a aerodynamic postural position. So as we go through this chapter, I want you to think of a couple of types of drag. There's what we call form drag. So write this down, form drag. And form drag is also sometimes called profile drag or pressure drag. So form drag, profile drag, or pressure drag. So the other type of resistance we get is from the surface itself. So in addition to form drag, we have what we call surface drag. So what are some things you notice about cyclists, especially their legs, that they do to reduce surface drag? Shave their legs, right? Because that hair can hold on to air molecules. So that's surface drag. What about their clothing? Is it nice and baggy? No. Okay, so they wear special clothing to reduce surface drag. The bike is also designed to slip through the air. So the way that the bike's designed reduces surface drag and form drag as well. Okay, all right, so let's take things to the water. So what are some things that swimmers do to reduce fluid drag? Yeah, okay, so that's good. You don't have all that hair and, okay, so that's surface drag.
The suits they wear.
Yeah, exactly. That's another thing, surface drag. So now might be a good time to play this clip, but at the 2008 Olympic Games, there were several world records set in swimming. Yeah. The LZR racer suit, designed by engineers at NASA. And 2 years after the Beijing Olympics, that suit was actually banned because it was just too fast. So you don't see those suits anymore, but surface drag is another thing. So let me, as long as we brought that up, that would be a good time.
Spacesuit from Speedo.
Space.
The Laser Racer, an ultrasonically welded, ultra-low friction suit that actually repels water. Developed by top
So keep in mind that you can't legally wear one of these suits anymore.
NASA in the wind tunnels used to check the aerodynamic qualities of space shuttles.
It's a lot of money going
We're
into
very
swimming.
privileged to be working with NASA. NASA obviously spend a lot of time working out the design of spacecraft and aircraft and how they can reduce friction on those vehicles. And we work with NASA in the same way to work out how we can reduce the level of skin friction drag created by a swimmer in a suit moving through the water.
The result is what experts claim to be the fastest swimsuit in the world.
In a traditional suit, there's a lot of skin movement. It just moves all over the place. So what these new suits are doing is actually controlling a lot of that extra movement. So it, again, keeps the water flow a lot closer to the body, makes it much more streamlined. So you move through the water a lot more cleanly.
Athletes wearing the Laser Racer therefore need less oxygen, meaning they can swim faster for longer. By scanning more than 400 elite athletes from around the world, Speedo's researchers were able to identify the areas on a swimmer's body that create the most friction. Then, by placing ultra-low drag panels on those areas, they were able to make each individual as streamlined as they can possibly be.
I felt like a rocket, like whenever, like right when I hit the water, I felt like a rocket. So I felt unreal. Can't wait to race in it.
I know Speedo puts so much time and effort and energy into developing the best suits, and knowing that they're getting scientists from all over the world and people from NASA, I mean, how can you question that's the best suit?
When people see all these great athletes lining up behind the blocks and with these great physiques, these futuristic looking suits on, it adds to the sport, it adds a new dimension to the sport, and I think that's exciting within itself.
The results have seen skin friction drag reduced by 24% compared to the Speedo suit worn in Athens in 2004, leading experts and swimmers to claim they are confident that more medals will be won and more world
Slightly.
records broken by Speedo athletes this year than ever before.
All right. Okay, so sometimes we use resistance, air resistance or drag resistance for training exercises. I think that's Adrian Peterson. How many have ran with a parachute? Yeah. So we can also apply that same thing to the water. Any former swimmers that swam with something like that to give you a little more resistance in the stroke. So we can do things to reduce drag resistance. We can also do things in training to provide an overload to increase drag resistance. So guys, we're going to study this. So what causes a baseball to curve? This is all about its interaction with the surrounding air molecules. So we'll talk about that. Soccer, ladies, what technique produces a banana kick? So it's kind of like a curved ball, only in soccer. Can you kick a goal from the corner? You seen that? Yeah, maybe we should do a lab out in the field. Maybe you could teach us all how to do a banana kick. It's pretty cool. So we'll talk about it. Talking about it is one thing. Actually being able to do it is another. Yeah. Okay. So fluid mechanics is all about the forces that fluids exert on objects or bodies that are flowing through them. So again, remember that in this chapter, we think fluid, well, it has to be just water. So we're also considering air as well. So air and water. So we do lots of things in sports to minimize air resistance, whether it be our clothing or our skin, the form that we adopt. Lots of things to allow us to go faster through air and water. So there's two different types of forces that are exerted on the body, flowing through air or water. The first one is a buoyant force. That's due to the object's immersion in the fluid. Buoyant force is oftentimes applied more to things exerted in water than air, but we'll get to that. Dynamic fluid force comes from movement directly into water or air. So one thing to remember is the buoyant force always acts vertically. So we can almost think of the buoyant force as a reactive force. I don't know what class is. Sounds like fun. So when we jump, we push into the ground. What does the ground do? That's the reactive force. So when we do tests on the force plate, what we're measuring is the reactive force from the ground. So a body or object immersed in air or water will have this vertical reactive force that's called a buoyant force. It always acts vertically. So it's in opposition to gravitational force that acts in the downward direction. The dynamic force is resolved into two components. So two parts. We have a buoyant force and a dynamic force. The dynamic force, in addition, has two parts. We call it drag and lift. So think of an event like the javelin. Lift is really important because the longer that javelin remains in the air, the further the displacement's going to be. So when we talk about lift, the angle of release is really important in order to create the greatest lift effect and keep the javelin in the air longer. So the first principle of this chapter has to do with a buoyant force. So it's called Archimedes' principle. So if I had a bucket of water and I had a beach ball and I pushed the ball under the water, what would happen to the level of water in the bucket? It would rise. So the buoyant force, what Archimedes' principle says is the buoyant force is equal to the weight of the displaced water. So when I push that ball under the water, it's going to displace a certain volume of water. And the weight of that volume that was displaced by the ball is equal to the buoyant force. So the weight of the volume of displaced water is equal to the buoyant force. Does that make sense, everybody? So we can think of a buoyant force as being like a reaction force. Now, because the beach ball itself weighs less than the volume of water it displaced, when we let go of the ball, what's going to happen? Yeah, so we've got the ball pushed underneath the water. And as long as we're pushing on it, that allows the ball to be under the water, and it contributes to that buoyant force. But as soon as we let go, because the weight of the ball itself is less than the weight of volume of water it displaced, it's going to come back up. So whether an object or body floats or not depends on its weight relative to the buoyant force. So how do we define weight? Going all the way back to January, if you don't know the answer to something, what do you say? Gravity. Weight is dependent on gravity. So you have these two opposing forces. You have weight, which comes from gravity. Okay, and gravity, does gravity still act on you when you're in water? Yeah. Okay, but with water we get a little bit of help from this buoyant force. So an object or body will float if the buoyant force is greater than or equal to an object or body's weight. An object or body will sink if its weight is greater than the buoyant force. So the buoyant force acts up, weight acts down. If weight is greater than the buoyant force, that object or body will sink. If the weight is less than or equal to the buoyant force, then we float. So another important concept that has to do with whether you float or whether you sink depends on density. How many have heard that term before? Density. Density. So let's talk about that. Density. The ratio of mass, or we can think of it as weight, divided by volume. So how much space? So if we look at the density equation, weight divided by volume is equal to density, total body density. So something that is very dense takes up less space for a given amount of weight. So is it possible that you can have two people that weigh exactly the same but have different volumes? Yeah. So that brings us into this discussion. So we have in this picture, we have a representation of 5 pounds of fat and 5 pounds of muscle. So exactly the same weight, but what's different? The density is different because of what? Volume. Which one has less volume? Takes up less space? Muscle. So you can think about it mathematically. If density is equal to weight divided by volume, less volume, like in the case of muscle, means greater density. So fat, for the same amount of fat, you have a higher volume, which does what to density? Goes down. Okay, so let's say you graduate from MSUB and you start your own fitness company and you have all these clients, you're making lots of money, and maybe you'll donate it back to us someday, but it's beside the point. So a lot of your clients are saying, well, my weight's not changing, but my clothes are fitting differently. So what would you say to them? Yeah, you're altering your body composition, right? So how are you altering your body composition? So your weight's not changing, but you're taking up less your space. Your volume is changing. So as you're building muscle and losing body fat, now don't take this as we can't convert fat into muscle and we can't convert muscle into fat, but we can change the ratio of those two. Okay, so if you're losing body volume because you're adding muscle and you're losing fat, okay, your body's becoming more dense. Your clothes are fitting differently. You're probably feeling better about yourself and your appearance because your body density is getting higher. So that brings us to another application. For the same amount of weight between fat and muscle, muscle takes up 15% less space. So muscle has 15% less volume for a given weight. So one of the criterion methods to assess body composition is the underwater weighing technique. How many of you have ever participated in that or had a chance? You don't see it very much anymore. That was kind of old school way back when. Tell you a story next class, different day. Because I used to have to clean the underwater weighing tank for my graduate assistantship. So we'll talk about that another day. But the way that the underwater weighing technique works is we're looking at the density of different tissues in the body relative to water. So if someone has a very high density, in other words, they have a high ratio of muscle to fat, are they going to sink or float? If you have a very low body fat and lots of muscle, you're going to sink like a rock. Okay, so muscle has greater density than water. Fat has less density than water. Air also has less density than water. Where are you holding the most air in your body? In your lungs. Okay, so one of the things that happens with an underwater weighing assessment is you're required to be under the water in this chair, and you have to blow out all the air in your lungs. And you have to hold still while you're doing that, which is one of the reasons why it's not popular anymore, because not many people like to be under the water for a long period of time with no air in their lungs and have to hold still. So you blow out all the air in your lungs because that contributes to a higher body volume, because air has less density than water. So just take this problem and you can just write on that sheet we're doing for today. So when Grant fully exhales, his body has a density of 1,020 kilograms per meter cubed. So all he has in, back up. So if you blow out all the air you can under voluntary conditions, do you still have some air in your lungs? Yes, we call that the residual volume. So what this says is he's exhaled all the air that he can voluntarily, which means his density is going to go up or down. He's going to have more density because he's gotten rid of as much air as he can. During a triathlon swim, Grant wears a wetsuit, and his density decreases to 990 kilograms per meter cubed. So what the wetsuit does is it increases his ability to float because his density is less. So Allie, are you allowed to wear a wetsuit for triathlon? Does that keep you insulated, kind of so your body temperature?
Yeah.
So, is there requirements on those like there is in swimming, or?
I don't know, I think so. Kevin just gives this to them and we wear them.
Okay. I had to ask him this. I had to learn more about triathlon. So the water he swims in has a density of 1,000 kilograms per meter cubed. Okay, so the first question, if Grant fully exhales, can he float in the water if he does not wear a wetsuit? So this is his density without a wetsuit, blowing out all the air in his lungs. This density is greater than the density of water, so what's going to happen? It's going to sink. Okay, so can Grant float in the water if he does wear a wetsuit? Yeah, so the wetsuit reduces his body or it reduces his density, so to be less than water, which allows him to float. Okay, so here's the density of different tissues and materials in the body. So air has a very low density, 1.2 kilograms per meter cubed at sea level. So as you go to higher elevations, the air becomes less dense, which if you're a baseball player is good, because the lesser density of air means what for the ball? You go farther.
It's not good for me, but
So water, as we said, 1,000 kilograms per meter cubed. Muscle and bone. So we call this the lean tissues of the body. The fat-free mass is referred to as muscle and bone, and they each respectively have a density of greater than 1,000 kilograms per meter cubed. And then fat has less density than water, less than 1,000 kilograms per meter cubed. So it floats in water. So how are we doing on time? Let's watch this one video here. So I did, my bachelor's and master's were done at Utah State and then doctorate at Arizona State, but this is at Utah State. This is the exact tank that I was assigned to clean for my graduate assistantship.
Hi, this is Dr. Dale Wagner. I'm an exercise physiologist at Utah State University. We're here in the lab this morning to take a look at body composition
So this is how this procedure works.
densitometry method, and we're going to use hydrostatic weighing. So we have two densitometry methods. One is the bod pod, and the other is this one, our hydrostatic weighing.
Notice that word densitometry.
With hydrostatic weighing, there are two important measurements that we need to get in order to do densitometry. We need to get body mass, which is easy enough to measure just with a scale, and then we need to get body volume, which is the whole point of putting someone in the tank and measuring them underwater. The hydrostatic weighing method works off of a principle known as Archimedes' principle, and Archimedes' principle basically states that if we put an object in water, in a tank or in a tub, a certain amount of water is going to be displaced. The amount of water that's displaced is equivalent to the volume of whatever we put in. And so that's how the underwater weighing procedure works. So we have our client.
So we're actually measuring body volume with the underwater weight.
Mass. The other information that we need to know beforehand, we need to know what's called the tear weight. That's everything other than the client. And so in this case, that would be our chair. Our chair is fairly heavy, so we need to have a baseline measurement of what our chair is. And on here you can see that if you can view the scale, you'll see that it's a 5, once the needle goes around one time, it's 5 kilograms. So you can see that the needle has already gone around twice. So we're at a little over 10 kilograms here. We're at 10.6 kilograms. That's our tear weight for the chair. One other thing that we need to know is the temperature of the water. We have a little thermometer in here. And so we just measure the temperature of the water. That's important because as the temperature of the water changes, the density of the water changes. And that makes it easier or more difficult for the subject to float. And so all that gets taken into consideration when we put this information into equations. We need to know the tear weight, the density of the water, and of course the subject's weight. Okay, Jen's
What I
ready
really
to
like
go,
about
so
Dr. Wagner is he's climbed Mount Everest. So he's awesome.
be careful. Okay, and she's just gonna have a seat on the chair. And the water level's right at her neck, so she doesn't have to bend too far. And the other important thing, there's two things that really makes a person float. That would be fat and air, okay? And so it's important that we try to get the subject to blow out all their air under the water. this is very difficult. It's an unnatural maneuver to do because naturally when you go underwater, you want to hold your breath. And so we want you to do the exact opposite. So when you go underwater, we want you to blow out as much as you possibly can. Once you think you have all your air out, try to push out just a little bit more, okay? Try to be as still as you can. The more that you move around under the tank, the more difficult it makes it to read the needle on the scale. Once you feel like you can't stay down there anymore, that you need some air, just come back up. I'm not gonna tap the wall or anything, it's all up to you, okay? So whenever you're ready. Yep. Blow, blow, blow. You can still see bubbles, so we know she's still blowing. And right now, she's finished. How was that? Okay. And we're going to try a few more trials, because usually what happens is people learn that they can blow out. They learn that they have more air than what they think, and they can blow out more than what they think they can. And once I don't see any more bubbles, then I take a quick look at the scale. And you can see there's a certain technique involved here. It's much more difficult for the technician to do underwater weighing than it is to do the bod pod, because you have to look at several different things at one time. I'm looking at the client to see when I don't see any more air bubbles, and then as soon as I don't see any more air bubbles, I have to take a quick look at the scale to see where the needle has stopped. So there's a little bit of a technique involved. It's a little bit more difficult for the technician, much more difficult for the client. This is a difficult procedure to blow out all your air under the water. And you can see that the scale stopped right around here. So on her, that would be about 12.6 kilograms. And obviously she weighs more than 12.6 kilograms on land. So you can see what there's a huge difference between your land mass and your underwater.
Okay, so that is it for today. Why don't you just leave your papers on the desk there, and then I'll come around and pick them up. We'll continue with chapter 8 on Tuesday.